Okay. So you're ready, right?
Yes.
Okay. So, and the entire committee, your committee is here. You can recognize them.
Yes.
Good. Okay. So, welcome, folks. Thank you for waking up early and coming for this. So, Utkarsh Soni will be defending his PhD dissertation titled Towards More Accessible Human AI Interactions in Sequential Decision-Making Tasks. His committee includes Professor Baral, Professor Brian, and Professor Wan Lu, of course, and I'm the advisor and the chair of the committee. And as per this week's Arizona Supreme Court ruling, the defense today will be conducted according to the antebellum procedures. So there may be some whipping involved in case the candidate fails the exam. The 1864 statute is somewhat unclear on who will be whipped. So, okay. Before we get started with the formal proceedings, I'd like to say just a few words about Utkarsh. Utkarsh started his PhD in spring 2019 in my group. Prior to that, he completed a master's at Arizona State University at ASU, I believe with the Ross's group, specializing in visualization. Although I still had to hammer on him that black background for slides don't quite work. I don't know what they teach in the visualization. He recently started as a data scientist at Manulife, very recently, and then after this, I guess after the successful defense, he'll hopefully go back there. During his PhD, Utkarsh has been involved in several impactful projects, both by himself and in collaboration with others. Google Scholar lists about 242 citations as of this morning. He will be describing some of that work today. In addition to the work he did with us in our group, he also continued his significant interest in visualization and did work with Chris Bryan's group. Although opinion is still divided on whether the catalyst there was his abiding interest in visualization or more about seeing a certain someone in Chris's group. As a person, Utkarsh is sort of an odd fit for our group. He's gentle and soft-spoken, characteristics no one ever associates with me or most of my group. And yet, some of his closest collaborations were actually with people such as Sriram Gopalakrishnan, who got done recently, who are at the other more normal for us end of the spectrum. For the longest time, he would be the quietest one in our rambunctious group meetings. So much so that Lin Guan once came to me and solicitedly told me, maybe we should have more polite forums so that Utkarsh will feel comfortable in presenting his stuff too. I'm proud to say that over the years, we managed to make him less gentle and soft-spoken. I remember him telling me that at an internship he was at, he found that he was the most outspoken and that it helped his visibility. While I could never quite tell how much he enjoyed the group meetings, I do know that he's been the facilitator for these meetings. For almost 2 years, he was the de facto meeting czar, recating the room, nudging the people to present, etc. This is perhaps in keeping up with his model citizen of the group role. I recall he, along with Sriram, completely took over and ran our group's participation in DARPA Ceylan program, in the process ensuring that our team did the best in one of the benchmarks we were responsible for. One other thing about Utkarsh is that he's perhaps the last of the small band of Yochanites who actually come to the lab in the mornings, which is when old people like me actually wake up. Most of the others wake up and stagger in well past noon. So when I came in the mornings, he would be the only guy I could get a chance to chat with. He was also absurdly conscientious, letting me know with full seriousness that he might be 40 minutes late on any particular day, when the rest of the bozos would skip town for weeks on without even a heads up. Another way, I guess, is somewhat different from the rest of the group. Utkarsh also used to provide a steady supply of Indian sweets, either through his travels or sometimes by a third party. There is this mango burfi that I took a liking to, and he made sure that we got almost regular supply of them. I almost expected it that he will find some way of finding them today too. Apropos of nothing, let me just say that I have gained higher gravitas during his time in the group. For a big guy, Utkarsh has a surprisingly light step and presence. One of the running jokes in our group is how Utkarsh will join group lunches or meetings and quietly slip away without any of us quite actually noticing. hey, where's Utkarsh was a common refrain, even when he is actually present at the table. I say this in part to warn you not to panic if he stages one of his what Kaya calls Irish goodbyes and disappears at some point during the defense. He's usually back. All in all, it's been a great having Utkarsh in our group, and we wish him all the best after this defense. Thank you.
Thank you. I also did notice his absence. He was always there.
Yeah.
And suddenly I didn't see him in the morning. Something wrong with the projector?
No, it come up. It's working in the morning. Yeah. Let me just reach.
So dark.
Yeah, no, it'll go. Thank you for your kind words, Dr. Rao. Okay, so welcome to my PhD defense for my thesis titled. Actually, I'll take a bit of water. So, welcome to my PhD defense for my thesis titled Toward More Accessible Human-AI Interaction in Sequential Decision-Making Tasks. So, we know that recently AI has been used successfully to solve increasingly complex tasks like self-driving cars, delivery robots, surveillance, etc. And there is an ongoing interest in adopting these AI agents into our day-to-day lives. Now, for this integration to be really successful, we not only want these agents to have be competent in the tasks they are assigned to do, but they also need to have certain broader capabilities, like they should be explainable and advisable. What I mean here is that if the user is confused by one of the agent's actions, the agent should be able to give an explanation for its action. On the other hand, there should be mechanisms through which any user can specify their preferences to the agent, and then the agent can align to those preferences. So here comes the objective of our thesis. Broadly speaking, we want to enhance the explainability and advisability of AI agents by defining this human-AI interaction process. And our focus is particularly on agents that are trying to solve a sequential decision-making task, meaning that here the agent is coming up with actions that will finally achieve some goal. Okay, so what's really challenging in this? So the problem is that most of the successful AI systems have used deep learning based representations to come up with the actions. So these representations or the features in this representation would obviously be uninterpretable or inscrutable to the user, and hence cannot be directly used for communication. So let's take a run-of-the-mill model-based reinforcement learning agent here, where we have a state image that is being passed through an encoder, which is a deep neural network, and there is some state embedding over which we have learned some transition dynamics. Now, this is well and general enough to solve this task. However, we have completely lost interpretability because the features that are in the state embeddings don't make any sense to the user and hence cannot be used for either explanation or preference specification. So the current go-to techniques in AI literature basically make do with communication over the only apparent shared medium between the human and the agent, which is images. So what's the issue with this? So explainable AI often employs saliency maps as explanation. And this actually works well for, let's say, one-shot decision-making task. However, what about this doesn't really translate to sequential decision-making tasks because here we don't have images, we actually have videos of the agent. Now, let's say you took some snapshots and you still generated some saliency maps. Great. But the problem is that the explanation would usually be tied to something in the environment dynamics. And just by looking at the image, it might not be very clear what part of the dynamics the explanation is referring to. Okay. Now, coming to the other end, how do usually these preference learning system advise an AI agent? So the current go-to techniques are reinforcement learning through human feedback, where basically we show the user a bunch of trajectories and they rank these trajectories based on their preference. And then we learn a preference function. However, you may notice that this is a very weak signal for learning. So these would typically require a lot of feedback from any user, and hence the scalability becomes quite a problem in this approach. So instead, in this thesis, what I'm trying to say is that the AI system and the user should basically interact with each other like us humans do via language. In particular, what I'm saying is, why not have a symbolic interface between the agent and the user, which will have a shared vocabulary or terms that both the agent and the user understand, and then use those to generate explanation and specify preferences. Now, another challenge in human AI interaction that is often overlooked is that of personalized interaction. In particular, each user can be potentially unique with different background knowledge, expertise, and preferences. So the communication system we have should be flexible enough that it can take the preference of any user that comes in. Finally, the explanations that we produce should match with the user's expertise level. So it's not too detailed, it's not too abstract. So to deal with all these challenges, here I'm presenting our framework for explainable and advisable AI. The core component in this framework is the symbolic interface between the agent and the user, while the AI's own model of the task can be completely inscrutable to the user. So this framework will have three components, and I'll talk about them one by one, where the first component is the explanation generation component, which takes terms in this vocabulary and generate explanations in those terms. The second component, in the second component, we put some additional constraint on this interface, and that allows our agent to personalize the explanation based on the current user's background knowledge of the task. The third and final component allows any user to add new terms in this vocabulary, thereby allowing them to specify any kind of preference. So I'll basically start by talking about this component in a second. Okay, so let's talk about this component. So let's start with a concrete example. Here we have an agent that is trying to solve the Montezuma-Revin's first level. The task is to get this key. And the state representation that this agent has are RAM states. So those features don't mean anything to the user. We also have the symbolic interface made up of a shared vocabulary. So these are basically propositional state variables, or what we call them concepts, that are either true or false in a given state. And each concept over here is grounded as a binary classifier. Now, in this scenario, we are dealing with answering contrastive queries from the user, where the user will say, hey, why did you go with plan X, the original plan, and not Y, which is the alternate plan or the foil? So there are two possible reasons why our agent in the first place preferred the original plan. One reason could be that the foil itself has an invalid move. So an invalid move is an action that you cannot actually execute in the environment, or it is, let's say, violating some hard safety constraint in the environment. So in concept of this game, if the agent dies. So that's one of the possible reasons. Another possible reason is that the foil is simply costlier than the original plan. So you can see that both of these explanations are actually tied to the environment dynamics. So our solution approach actually involves learning a symbolic representation of the dynamics, which we'll use for explanation. All right. So this symbolic model consists of three sets. First, is a set of fluents or propositional variables that are coming from the shared vocabulary. A set of actions A, where each action is described with basically a set of concepts which are preconditions for that action. So these preconditions must be true in a state for that action to be executable. Finally, we have a cost function that tells us, okay, this action, given the presence of these particular concepts, will cost this much. With these components, if we have access to these components, we can actually generate explanations such as this. So let me just explain via a little concrete example. So this is the original plan. The agent says, I'll go down to the lowest platform, I'll jump over the skull and then I get the key. The user says, in this particular state, why not take an action left and just go through the skull? So if the agent knew the preconditions for the action go left, then they can say that move left action will simply fail because one of the necessary precondition is that skull not on left should be true in this state. Okay. Similarly, we can also basically invalidate suboptimal foils. For this, in this case, the user says, hey, why don't you just attack the skull and kill it? In this scenario, the agent can say that the attack action costs at least 500 when skull on left is true in a state, thereby making the total cost of the foil greater than the cost of the original plan. Okay, so ultimately what we really need are some preconditions for some actions or some cost function abstraction to generate the explanation. Okay, so I'll basically talk how we can get the precondition, but for cost function, it's detailed more in the thesis. So how to learn the precondition? So let's start. What we do is we start with the foil that the user has presented and we take the first state which has an invalid action. So we denote it as S fail and the action that was suggested as A fail. Then what we do is very simple. We basically take the state S fail. We see what are the concepts that are actually missing from this state because one of them is the precondition concept. So this is the hypothesis set. Then we sample states around the original plan and the foil. And then we take all the states where that action A fail was actually executable. Once we have this, what we do is we see what are the concepts that are true in these states. And the precondition concept would obviously be present in both this state and the hypothesis set. So we take the intersection. So with a large enough n, eventually you will only have the precondition concept remaining in this set. Okay. One of the more important things that we want to tackle here is that the user should be able to put their trust, how much they can trust this explanation. For this, we basically computed a confidence score in the generated explanation where we created some probabilistic graphical models to compute this. These models basically consider two things: correlation between concept and noise in the concept classifier. So here is a more simpler version of one of the models we consider, which is basically saying this, that a concept C is present, if a concept C is present in a state S, there could be two reasons for it. One, that action A is executable in state S, and that concept C is a precondition for that action. The other reason could be that it is simply correlated with these other concepts in the state. So just because we are noticing a concept C in a state doesn't necessarily mean that it is a precondition, and this is what we are modeling. So the detailed formulas are in the thesis, but here is an abstract version of one of the simpler cases where we assume we have a perfect classifier. In this case, when we sample a state S and we find that action is executable and a concept C is present, then the probability that the concept C is not a precondition of A is simply directly proportional to the probability of concept C in this state given all the other concepts that are in that state. So this is basically correlation. What this is intuitively saying is that if you anyway notice this concept with all the other concepts in that state, it's not a strong enough evidence that the concept C is a precondition for it. And in scenarios like this, you would have to keep on sampling till you keep observing this concept C till your confidence becomes high enough. So we basically modified explanation generation procedure to pick model components now, which have the highest likelihood of being true. Okay, so going quickly over the evaluation, we evaluated on Montezuma revenge game and Sokoban game. This is also a game where the robot has to push a box to the target. We had a total of 7 foils, 5 were invalid, 2 were suboptimal, and in all cases, we identified the correct explanation. Moreover, as we keep on sampling more and more states, we can see that the confidence in our explanation increases, which is also dictated by the models. Finally, we also did a human subject study where we wanted to see, is generating symbolic explanation even useful? So what we did was, we compared symbolic explanation that establish model components over certain simple explanation, where we, to refute an invalid foil, we'll just say that, hey, this action is invalid. We won't say what precondition is involved. Or for cost, we won't say what concepts are involved. We'll just say that this is the per step cost of each of the steps in the foil. So we actually found that, in fact, people prefer symbolic explanation that give us certain model components that are involved in the in why the foil was invalid. And the result was statistically significant. The final user study we did, in this study, we basically saw if concept-based explanation provide a better task understanding than saliency map-based explanation. In this case, the participants played the Sokoban game and were given an explanation whenever they took an invalid move. So this was a between subject design where participants were given either concept-based explanation or saliency map-based explanation. And we did find that, in fact, with concept-based explanation, the users were able to quickly grasp the task dynamics, and hence the total time taken and the total number of steps to complete the task was significantly lower. So this brings us to the end of the first component, where we generated some explanation. Okay. So now I'm going to talk about our second component, which allows us to personalize explanation based on user's background. So far I have not talked about this, but we have been actually dealing with explanations that are commonly termed as model reconciliation explanation that were first introduced by Chakrabarty et al. So these kinds of explanation deals with scenarios where the robot's model of the task differs from what the human's expected model of the robot is. Due to this model difference, the plans that are optimal in the robot's model will still maybe suboptimal in the human's model of the task. So let's take a simple example here. Here we have a task where the agent has to go to this goal location, and it goes to do that, it goes over a puddle. And the user is confused with this transition because the user thinks going over the puddle can damage the robot. So there is a cost associated with this action in his model. So the robot must give an explanation saying going over the puddle incurs no cost. And after this model update has happened, this plan would, or this transition would become explicable to the user. So we are interested in coming up with such model updates. In fact, the symbolic explanation discussed in the previous component in the framework were also model updates where we were updating the precondition of actions. Okay. So in this framework, we are particularly dealing with scenarios where each user can have a different model of the task and hence require explanations that are tailored to that model. Now, we make a simplifying assumption here that actually there are types of users such that users of same type will have similar model of the task. Hence, the explanation should be personalized based on user's type. So here is an illustrative example where the robot's task, this is a disaster rescue domain, and the robot's task is to pick up this victim, move them to the shelter. And there are two types of users. User of type A believes that picking up this first aid kit is unnecessary. User of type B believes that going over the puddle can damage the robot. So they clearly require different updates. So what's really challenging in this? The first challenge is that we do not know from the get-go what are the different user types that exist for the task, and their model of the task is unknown, which is necessary to generate explanation. This is something that we solved during the training stage using clustering. The second challenge comes when the robot will actually interact with the final target user and explain some plan. This is what we call interaction stage. And here, the challenge is that we do not know what is the type of this user. And whenever we are generating explanation, there is a communication cost. Whenever we are showing a plan that is still inexplicable, there is an inexplicability cost. And we need to balance both these things. Okay. So before going into the detail of the procedure, I want to point out how we actually approximate the model of a given time. And for this, we simply follow the model approximation presented in Sarat et al., where we assume that we have access to a set of explanatory messages E, where each message corresponds to some symbolic information about the domain parameters, the actual domain parameters. For example, one of the messages could basically represent the fact that the reward for going into a state with puddle is actually 0. So there is no negative reward or there is no cost for that action or that transition. Once we have this set, we can basically approximate the model of any user by learning what we call a labeling function, which maps a transition, state, action, next state, a set of messages to either 0 or 1, where 1 means that the labeling function, the type that this labeling function belongs to, will find this transition to be explicable given this message, and 0 means they'll find it to be inexplicable. So we can basically, with such a data, we can use any ML technique to learn the model. Note here that once we have given this set E, the technique that I'm going to present is agnostic to the actual task representation. So it's compatible with the framework. So here is the training stage. Recall here that the objective is we want to learn model of each possible user type for the task. So to do this, you basically collect training data from a set of observers where the data is of this form. We have transition, we have messages, and we have labels. And essentially, we take all the observers and we cluster them directly into user types. The detail of this procedure and thesis, but the core trick we use here is that we project each observer as a vector theta naught, where theta naught represents an estimate of the set of messages that when given to that particular observer will make any transition appear explicable. So it is kind of a proxy for what their model is. So in this embedding, observers from same type would be closer together because they have similar model of the task. So we perform clustering in this embedding. So here we have clustered all the user types. Then we basically recover the original data that belong to each of the observer. And then we learn, so these are the 3 identified types. So we learn the labeling model for each of the type with this data. In this particular case, we additionally learn a confidence measure that gives us the probability of an explicability label given a transition in a message. Okay, coming to the more fun part, now we actually come to the interaction stage where we want to explain any plan pi to a user whose initially type is unknown. So this interaction happens in steps, where at each step we'll present them a plan prefix. We'll give them some explanation. This can be empty. And on the other side, the user will tell us which transitions they found to be explicable and which transitions were confusing to them. And that actually serves as an evidence for what their actual type is. Moreover, what we are trying to optimize here, if you recall, is the total cost of interaction, which is a linear combination of communication cost and inexplicability cost, with lambda as the trade-off parameter. Okay, so what we want to do is reason about the unknown user types, optimize the cost of interaction. So we can simply compile this problem as a POMDP or a partially observable Markov decision process. In this POMDP, the user's type becomes the unobservable variable. The reward function captures the cost of interaction, and the actions that the agent can take are at a high level explanatory messages that the agent can give. So finally, solving this POMDP gives us a policy over belief state. where in this case, the belief state is simply our estimate of the probability distribution of the possible user type for the current user. So this is saying that there's a 60% chance that the user is of type B. And in this case, we'll have a policy as to what explanations we should give to the user. So now all we have to do is when we get labels from the user, we'll have to update the belief in each type. So the probability or belief that the user is of type T is simply directly proportional to the probability that the user of that type T will give you that label Li, where if you recall, we learned this exact thing during the training stage. So to sort of highlight why did we actually go with the POMDP, let's take a very simple scenario where the agent has to explain a plan and the very first transition in that plan is actually explicable to user of type A and inexplicable to user of type B. In this case, instead of giving some explanation, the POMDP policy can withhold explanation completely and then just see what label do we get from the user. If it is explicable, we'll know that it is of type A. If it is inexplicable, we'll know it is of type B. And further down the line, now we can personalize the explanation. So this is why we used POMDP, because it can take information gathering actions, which can reduce uncertainty in this belief. Okay, so the problem with POMDP is that they are kind of computationally expensive. So we use QMDP and POMCP solvers, which are approximate solvers, and we had our own solver. For evaluation, we evaluated over disaster rescue domain and 4-room domain, where we varied the number of user types between 2, 3, and 4. We varied the communication and inexplicability trade-off parameter lambda, where we generated 3 plans per lambda and generated explanations for each user type. And the final evaluation metric was a regret measure that measures the difference between the cost that our solver has minus the cost of an Oracle solver, which already knows the correct user type. So here are the numbers. Over here, you can treat lambda as basically cost of one explanatory message. So here are the Oracle cost, and we can see that both QMDP and POMCP technique don't have too much regret, meaning they did not put too many extraneous explanations and were in fact able to personalize the explanation as compared to baseline. So there we also did a user study where basically we wanted to see if personalizing explanation is actually useful for the end user or not. So here it was a between subject study over the disaster rescue domain, where we generated 2 kinds of explanation. One was personalized and the other was conformant explanation, where conformant explanation is simply that if we have a transition, we'll basically give all possible sets of messages such that that transition would be explicable to any user type. With this, we actually saw that personalizing explanation can reduce the total interaction time that we spend with the user. It has much less inexplicable transition. And finally, we also quizzed them, where we found out that the model retention, the explanation that we gave them, they actually remembered them more in case of personalized explanation than in conformant explanation.
How did you measure that they remembered it?
Oh, so we basically quizzed them in the end. Okay, so this brings us to the end of the second component. All right. So I'm now going to talk about the third and final component, which allows users to add new vocabulary terms to this interface. So going quickly over the concrete example, here we have an agent that is trying to solve the task of Minecraft, where it has to create a ladder. In this scenario, there are 2 ways. One, it can pick up these sticks, craft a ladder and put it at the target, or it can go in this storage location given by this green box, pick up a broken ladder, repair it and put it at the target. Now, in this scenario, we have a symbolic interface for communication, And this user actually has a preference where the user does not want this robot to go into the storage area. So the relevant concept to specify this preference is avoid state where in storage area is true. Now this symbolic interface already has some concepts in it, but this concept in storage area is missing. So that's our objective, that we want to learn concept roundings online on the fly while minimizing the feedback required by the user. So the bigger challenge here is, first of all, we're going to ground these concepts as concept classifiers. So we need positive and negative examples of concept. And if we did a naive thing like randomly sampling states from environment and asking for their labels, in that case, it can be very inefficient if the positive concepts are very rare in the state space. Instead, our solution involves gathering likely positive and negative examples of the concept and then clarifying their label from the user. So to gather these likely positive and negative examples, we make certain assumptions. The first assumption is that we are already given some precedence relation between concepts, where this precedence relation is a directed acyclic graph from a path that has a path from the target concept that we want to learn to some known concept that is already in the vocabulary. And there can be multiple intermediate concepts between target and known concepts that are not in the vocabulary. Yes.
So those are examples of concepts like in storage area. And suppose we have like not in storage area. Is that a concept?
So we can add that in the vocabulary.
Should be a separate one.
Yeah, because once we have a classifier, we can easily just negate, learn the negation of it. And they can also be compound concepts. So as long as we have these atomic concepts, we can create any kind of compound concept like A and B, A or B, things like that. So our focus is more on these atomic concepts. So in this precedence relation, basically each edge Cx to Cy represents a precedence relation, which is basically saying that for Cy to be true in the next state, Cx must be true in the current state. The other assumption we make is that if a concept is true in a state, then it would be likely true in the states around that state, original state, and that positive examples are rare in the state space. The final assumption is we have concept region locality, where we are saying that if we are given any positive example, then there would be some localized region in that image which indicates the presence of that concept. With this, we can define our solution approach, which at a high level, here are the two components of our approach, and then I'll give the final approach over here, and then that's evaluation. So the two components of our approach are this. First off, we are given like a precedence relation Ct to Ck. Ck is known. So there are two ways. So what we do is we first collect some seed examples of Ct using this precedence relation, where we basically sample trajectories from the environment which end in the concept Ck being true. So we know that in the penultimate state, Ct would be true. So that's a seed example of Ct. Once we have that, we have two unique ways of expanding this seed example to finally learn a classifier. One way involves basically using informed queries, where we do random walk around seed examples and query the label from the user. In the second case, for negative examples, we just rely on randomly sampling state. And then on the collected data, we train the classifier Ct. So the classifier trained using this way is what I'm calling C star classifier. On the other hand, we have estimated labeling procedure as well, in which we start by asking some patch queries from the user, where we ask the user to annotate a patch that is telling us the presence of a concept in an image. In this case, we do template matching, where we'll now go in the state space and we find states with similar patches, we'll mark them as positive, and states which don't have such patches, and we mark them as negative. And then we train a classifier on this estimated labeled data. We have very few iterations of improving this classifier's accuracy as well using active learning. So the classifier learned using this way is what I call C hat classifier. And if you would notice that this actually has estimated labels where this does not. So the amount of feedback required here would be much less than the amount of feedback required here. but it could be more noisier. Finally, I want to point out that we don't train CNN from scratch. We use pre-trained vision language models for learning any concept classifier. So we fine tune. This brings us to the final approach. And this would be the last technical slide. And now there's only evaluation. So in this case, this is a more general chain we have from CT to CK with multiple intermediate concepts that are not known. So our approach to learning CT is to basically sequentially learn this intermediate concept and then use that to learn CT. So this is where adaptive learning kicks in, where we start by obtaining some seed examples of C3. Then we'll learn C3 hat, which, as I said, requires less feedback. And we'll use C3 hat to get the seed examples of the predecessor concept. However, online, if we find that C3 hat is not really accurate enough, then we'll adopt and we'll learn the more feedback intensive C3 star. So in the best case scenario, we can get away with just training C3 hat, which requires less feedback for training these intermediate concepts. Finally, we would have some seed examples of CT and we can learn CT star. Once we have this, we can actually now modify the underlying MDP to adhere to users' preference, as we'll see shortly. So now coming to the evaluation, we first did some ablation experiment to see if using vision language models is actually helpful, if is adaptive learning model reducing feedback, and more importantly, we compared our technique against the current go-to methods of preference learning, which is preference-based reinforcement learning approach, or PBRL, more commonly known as RLHF. So we did computational experiments and user study. So just to recall, in PBRL approaches, the way they learn preference is by giving the user two trajectories where they say which one do they prefer. So these were our experimental setting. The evaluation was done on Minecraft domain with the target concept in storage area. We had three settings with different number of intermediate concepts. And these are our ablation experiment results. Basically, we have 4 techniques, depending on whether we have adaptive learning, training only C-star type classifier using vision language model. Here we fine-tuned CLIP and using a CNN from scratch. So without too much detail, basically we varied the query budget and computed the F1 score of the target concept in storage area. And we find out that, yes, in fact, as expected, using CLIP gives us a much better classifier, much more efficiently. And we see that this blue curve is actually adaptive learning with CLIP, and that performs the best, and it is able to very quickly train the very good classifier. So we also compared, as I said, with PBRL approaches. So to do that, we had to first train a preferred policy using the concept classifiers that we have learned so far. So to do this, we modified the underlying MDP to give negative reward whenever the agent was predicted to be in the storage area. And then we simply trained an RLH. So in this case, for each setting, we trained the agent with a concept classifier which had the maximum F1 score with minimal feedback required. So this turns out to be a total feedback of 80, 140, and 150 with 0, 1, and 2 intermediate concepts. And in fact, we were able to train a policy that does achieve goal without going into the storage area. So this corresponds to a total reward of 3. On the other hand, we also trained a policy using PBRL, where we designed an oracle user, which when given 2 trajectories, will pick the trajectory where the agent is closer to the final goal. In this case, with ranked trajectories, we train a reward model, and then we train an RL policy over it. In this case, what we found was that actually it took significantly longer feedback, around 50K, to train a more policy that has similar performance to our case, which only had like 150 feedback. So what we are trying to say here is that if you already have some vocabulary, then expanding that vocabulary can be much more efficient given you have some precedence relationships. Finally, one of the things that bothered me was that while we were comparing the number of queries we make versus PBRL makes, the nature of both of these queries are very different. In one case, we are asking the user, is a concept present in this state? In the other case, we are asking them to compare 2 different trajectories. So what we wanted to do was see what is the cost of these two query types. So we did a human subject study where we had a very simple task for the agent. The agent had to simply go to this goal location while avoiding going over this green square which represents carpet. And the participant's task was to guide the robot for this preference. So this was a within subject design where participants were given both these query types, where this query asks the user, is the agent present on the carpet? So these are the kind of queries we make. And these are PBRL queries, where basically so basically we showed them two clips and we asked them which clip is better.
So with that, what the within subject was?
It was a within subject study where participants were given like 10 queries of each type. So we did interleave them. So first it was randomized. They'll either be given a sequence of concept queries and then PBRL or the other way. So what we did was, for evaluation, we compared like what was the average time taken to answer each query. And we also compared the cognitive load of query by NASA TLX score. So the average time taken to answer PBRL query is around 5 times than average time taken for concept query, result being statistically significant. And for NASA TLX, we have these 6 dimensions. For each dimension, we directly ask the user to compare the query. So we ask things like which task felt less mentally demanding. And we can see that in all the cases, majority of users preferred the concept query, with these results being statistically significant. So this brings us to basically the end of the core projects or papers that I was involved in. And just to summarize, we basically are saying that there should be a symbolic interface between the agent and the user for communication, even though the AI-owned model can be inscrutable. And we saw 3 components: one which could generate explanation using these terms, one which could actually personalize explanation based on user's type, and a third where the user could add new terms and it would specify their preferences to the agent. So these are all my research papers that I was involved in, my current Google Scholar. And before I open to questions, I want to take a few minutes to quickly acknowledge everyone. So I want to start by thanking Dr. Rao, and I have like a lot of gratitude for him for always being like supportive, and basically I could always rely on him on any research advice or any career related help that I could find. I don't take that for granted at all. I would like to thank my committee members for their time and considerations and their feedback, whatever feedback I was given. And I would like to thank all my lovely lab mates. They have truly inspired me and have always positively impacted in the quality of my work, and also have dictated my work ethics. So to kind of summarize what I have taken away from my lab mates and Dr. Rao is that I have a principle that I want to be as hardworking as Yantian, and as academically rigorous as Sarath, as enjoy my work as much as Dr. Rao does, and be as handsome as Albert. Okay, so yeah, I'm ready to take
Any questions? I think public questions and committee can ask either right now also. Please.
Regarding the second module of the work, where you are learning personalized user explanations, I understand that you are assuming you already know all types of models that the users can belong to.
No, we're learning that from data.
But you would still classify them in one of the models.
Yes. Oh, yeah. So we don't allow for learning like new models. Our basic assumption is that given enough data, we can learn all possible user types from the start. So we don't really accommodate for adding like new types. But yeah.
So.
But things like non-parametric clustering or things like that can be used. So like Chinese restaurant probably quickly learn.
So the question is, what are the assumptions you are making regarding what knowledge you have about the domain of the task that you could exhaust all possible types?
No, so we are completely relying on like having a large enough like observers in the beginning that we can make that assumption. There's no guarantee, but we are assuming that we have a large set of observers in the beginning, and they do like basically cover all possible user types.
I reward you a bottle of water. You run out of water, right?
Yeah, thank you. Yeah, that's a quick question. So, have you ever found like some domains or tests that like these kind of explanations are not necessary or even like impaired, like during the study of?
So the whole point of explanation is that the model of the domain that the user has can be different from what the actual model is, and these kind of model discrepancies can always happen. But if like it's a very commonly known domain, we probably don't need very explanation procedures. But it's always good to have this kind of thing in, because then like it's very like assuming that every user A has the same model of the task and has the exact correct model is also something like a very stronger assumption for any.
So you demonstrated this on mostly like discrete domains like grid worlds. Do you think it would generalize to say like real world domains, like say
The sector person, yeah. I mean, so the thing is, most of our cases, as long as we have a trajectory and we have a simulator, all of our components can directly be applied there. For example, for our for the second component, right? If all we really need are like trajectories. Once we have that and some like a starting explanation set, once we have that, we can essentially adopt to that domain. So it's really very agnostic to what the whole the representation is.
Another question is like how, I think maybe someone else touched on this, but like how do you establish your starting vocabulary?
Right, so that's a good question, and we basically, so first off, the whole third component is about adding new terms to the vocabulary, because it's kind of unreasonable that the domain designer would know all the possible vocabulary terms from the get-go. But one of the things that we did explore in the first component was that we actually did human subject studies, where we let the user play the game, and then like a bunch of users play the game, and then they came up with what concepts they thought were relevant for the domain dynamics. So if you do something like this, you can very essentially cover all the important concepts that do exist. And in the first particular domain, we do have mechanisms which can tell us when that vocabulary is insufficient. And the third one actually lets you expand that.
If there are no other published questions, then we can shift to so yeah, have some food and
Stop recording. Doctor, stop recording.
yes, you have.
And also, you don't want to graduate, right?
Yeah, because you sent proposal slides, I didn't notice. In the subject line, you sent slides.
I noticed.
Not systems defense, huh?
We can take you on your word.
So,